Hi, Physics 1, Mr. Janowski here. We're about to start the videos for the slides for Chapter 10, Rotational Motion, which we had started in person and for real in the classroom back in the day, back when we were real people in the classroom. But we're going to kind of take it from the top here again. So here is the beginning of Chapter 10, Rotational Motion. So I'll try to go quick. I say that every time, but this time I really will try to go quick. So yeah, think of an example of a time when you learned something difficult, and then later you learned a similar thing, but it was easier because of having learned the first thing. Well, this is what rotational motion will be, hopefully, because a lot of this stuff is very, very similar to the things we learned before, especially kinematics. And that was difficult, and this is difficult, but hopefully this is going to be easier because you've already learned the other similar thing first. And do you have any cousins whose immediate family is analogous to your own? So the idea of cousins being analogous is going to be very important throughout this chapter, as we'll see in the slides coming up. So rotational motion, chapter 10. So linear and rotational motion are cousins. That means they're analogous, but not everyone knows the word analogous, or at least it's not in their everyday vocabulary. So instead, I'm going to keep saying cousins. So for every linear quantity we've learned, there is an analogous rotational cousin. So the rotational cousins are a little bit more difficult to visualize than the linear ones, which makes it a little bit more challenging. But again, back to the first point from the do now thing, hopefully by having learned the first stuff already, the regular kinematics and that kind of thing, learning this stuff, even though it is also difficult, will be easier. We'll see. So yeah, quickly, some of the cousins. So on the linear side, we learned displacement, or it's also called position. That was x, and then there's regular velocity v and regular acceleration a. And these guys all have rotational cousins. So the cousin to linear displacement is angular displacement, theta. The cousin to linear velocity v is angular displacement. This is omega. This is a lowercase Greek omega. And the cousin to linear acceleration, how quickly you're changing velocity in a straight line, is angular acceleration. And this is an alpha, a lowercase Greek a, essentially. This is how quickly you're changing angular velocity. So these guys are all cousins. And for every single kinematics equation that we learned way back in the day, there is a cousin rotational kinematics equation. So all of these guys over here are all the same as these guys over here. The only difference is I replaced all of the things with the cousins. So every x became a theta, every v became an omega, every a became an alpha, and t is its own cousin. Time is time, that doesn't change. So yeah, these equations are just exactly the same as these equations, only they're the cousins. So for all of, keeping with the idea, all the linear quantities, there is a rotational cousin. So the cousin of mass is this weird idea called moment of inertia, which is a capital letter I. We won't do a whole lot with that. The cousin of force is torque, which is designated by a lowercase Greek letter tau. So this is a lowercase Greek t for torque. So the most important thing you will learn in physics all year, F equals ma. That's Newton's second law. Well, there's also a Newton's second law for torques, and that is tau equals I alpha. So I just replaced all of these terms with their cousins. F becomes tau, m becomes I, and a becomes alpha. There's also angular momentum, which is designated by an L, and just like P equals mv, well, think of the cousins of those things. L is equal to I omega. So I is the cousin of m, omega is the cousin of v. There's a formula for work. Work equals Fd cosine theta. There's also a formula for work on the rotational side. Work equals tau theta, which we're not actually going to do a whole lot with this. And just like there's kinetic energy, sometimes called linear kinetic energy or translational kinetic energy. That's the kind of kinetic energy you have from moving in a straight line. There's also rotational kinetic energy. And this is 1/2 I omega squared. And just like work and kinetic energy over here have units of joules, work and kinetic energy over here also have units of joules. So useful things to know. The formula for arc length, S is equal to R theta. That's the most useful. Well, occasionally we'll use the other ones. The other ones are saying V tangential is equal to R omega, and A tangential, tangential acceleration, it's not angular at all, tangential acceleration is equal to R alpha. And these only work if your angles are in units of radians. So this would be in radians, this would be in radians per second, this would be in radians per second squared. There's also ones for period, frequency, and angular frequency. T is a big time. It's the period. It's the amount of time it takes something to go around once, to do a lap, for example. And frequency is how many laps it does per second. Well, frequency is the inverse of period. So T equals 1 over F. And if you solve that for F, you get F equals 1 over T. And this one, you're not going to see this in my class, but this will come up in college sometimes. A different way of thinking of frequency, instead of cycles per second, it's radians per second is basically what this is. Omega is equal to 2 pi F. And there was also a formula for centripetal acceleration. A sub c, A centripetal, is equal to V tangential squared divided by R. So we have to be able to think of radians very well. So what exactly are radians? Depending on the math class you're taking, you may be dealing with radians a lot in that class too. But just like degrees, radians are just another way of measuring angles. So we tend to like degrees. When we first learn angles, we think of them always in degrees, and we tend to prefer to think of them that way. It turns out for some types of maths, which is how the British would say it, radians are a much better way to measure angles than degrees are. So a radian is a unit of angle. This is, the difference between degrees and radians. It's kind of like measuring something in feet versus measuring it in meters. It's just a different unit for measuring the angle. So what a radian is, it's the angle you get if you go out from a circle. So the GIF is there now. Go out from the center of a circle, 1 radius. Go along the edge. So this is an arc length of 1 r. And then go back to the center. And this angle you've cut out here is an angle of 1 radian. So 1 radian is about equal to 57.3 degrees. It would actually be irrational. It goes on forever, doesn't repeat, but it is about 57.3 degrees. So here are some of your common angles, and their equivalents in radians and also in revolutions. Revolutions are another way of measuring angles. It seems kind of strange to think of them that way, but that's what they are. So if you are, well, depending on the math you're taking, you may be studying the unit circle now, or you may have studied it already. But, these are just some of your common angles. So 30 degrees, picture what that looks like. Well, how many radians is that? That's pi over 6 radians. How many revolutions is that? That's 1 over 12 revolutions. That's 1/12 of the way around a circle. And, these are all the common ones. I'm not going to do them all. Well, let me do this other important one. 90 degrees, so a right angle. How many radians is that? That's pi over 2 radians. How many revolutions is that? Well, that's a quarter of the way around. You might start here and roll up to here. You've gone 1/4 of the way around the circle, so that's 1/4 of a revolution. And all right, let me highlight this one too, because this one will actually be important. This is the one we'll use to do our field goal post when we need to change units. 360 degrees is the same thing, has 2 pi radians, and that's the same thing, has 1 revolution. So again, this idea, revolutions are just another way of measuring angles. Seems a little bit weird to do that, but that's what it is. So for example, when I'm ice skating, which I haven't done in a while, and now the rink is closed for social distancing, but I'll get back there eventually. So I can ice skate a little bit. I can spin around, but not very well. If I go about 2.5 times, I get very dizzy and I fall down. So 2.5 times around, how many degrees is that? How many radians is that? So what kind of problem is this? This is a field goal post problem. So we know we're starting with an angle of 2.5 revolutions. So again, revolutions are just a weird unit of angle. So if I want to figure out how many degrees is that, I need field goal posts to get me out of this unit and into the unit I want, which is degrees. So I take this idea and I use it to make field goal posts. So I want to get out of revs and into degrees. So that means I need to put revs on the bottom and degrees on the top. So 1 revolution is 360 degrees. Remember, that's the other idea when you're doing field goal post, is the thing on the top has to be equal to the thing on the bottom, just in different units. So yeah, you do the math, you end up with 900 degrees. How many radians is that? Same idea. Just start with 2.5 revs and then use field goal posts to get you out of revs and into radians. So 1 rev is the same thing as 2 pi radians. So cancel the revs. This will give you your answer in radians. When you do this, 2.5 times 2 pi gives you 5 pi radians. However, in physics, we don't want you to write it as pi. We want you to write it as a decimal. So 5 pi radians is about 15.7 radians, because pi is 3.14 and 5 times 3.14 is 15.7-ish. I'm rounding, obviously. So the cousin of displacement x is angular displacement theta. The units of theta are radians. Well, they can also be degrees, they can also be revs, but we're going to usually want to have them in radians for the problems we're doing, especially the kinematics problem. So think of the other cousins. The cousin of velocity v is angular velocity omega. So don't call it w, please. Call it omega. I know it's just a script w, but call it omega. So yeah, the units of velocity v are meters per second. Well, the units of its cousin omega are radians per second. And this idea here, v is delta x over delta t, I would call this your basic definition of velocity. If that's true, then think of what must be true for its cousin. The basic definition of omega must be delta theta over delta t. And same idea down here. So we know a, acceleration, which comes in meters per second, its cousin is angular acceleration, alpha. So if a comes in meters per second squared, alpha must come in radians per second squared. So if this a is delta v over delta t is your basic definition of acceleration, then your basic definition of angular acceleration must be alpha is equal to delta omega over delta t. See all the Greek you're learning? So this formula is also going to be very useful at times. This idea, your basic formula for arc length, S is equal to R times theta. So if the circle rotates through some angle theta, could be less than a complete revolution, could be many, many revolutions. But yeah, if it goes through an angle of theta, a point a distance r away from the center is going to go some distance s, and s is equal to r theta. And this only works when your angle theta is in radians. This is the beauty of radians. This is why radians are useful. So if you're watching this GIF down here, notice this is like a rigidly spinning disk, so the whole thing has to spin together at the same time. Every point along this disk has the same angular velocity. It's all going around at the same rate, so it's got the same omega. However, different points along this disk are going different distances in that same time. So if you're looking at a point all the way on the outside, every time this thing goes around, it has to make this big circle here. So it's going a big distance d. If you're looking at a point closer to the middle, like this guy here, every time it goes around, it makes a much smaller circle. So it's going less of a distance d. So your basic definition for v, is delta x over delta t, delta d over delta t, same idea. So that's your basic definition for v. Well, in that case, this is like your tangential velocity. You're going a greater or lesser distance in the same amount of time, so you've got a greater or lesser tangential velocity. So yeah, your formula for tangential velocity, tangential is a fun word to say, and that is how you pronounce it. It's not tangential, is v sub t is equal to r omega. So Beatles reference. We've got 4 Beatles standing on a vinyl record, and the record's going around at 33 1/3 RPM. So all of our Beatles are different distances from the center of the record. So we want to calculate omega, the angular velocity of this thing, and then we want to calculate the tangential velocity for each of the Beatles. So if you don't know the Beatles, shame on you, but here are the Beatles. Here's George. George is now dead. Paul is still alive. Ringo is still alive. And John died a long time ago. So we're down to 2 out of 4 Beatles. So all of these Beatles are standing on the vinyl record, and the record is rotating at 33 1/3 RPM. So we want to calculate omega. We want it in radians per second. So 33 1/3 RPM. Well, what is that? RPM is revolutions per minute. So it's an angle in revolutions per a time, minutes. So, we already have n omega, we just have it in the wrong units. So the omega that we're starting with is 33 and a third revs over minutes. So first, let's get it out of revs and into radians. So use your field goal post that gets you out of revs on the top. So we had revs on the top, so we want revs on the bottom, radians on the top. And then this other one might be a little tricky. We were in units of per minutes as far as the time goes. So we already had minutes on the bottom. So to get out of minutes on the bottom, the field goal post for that, we needed to have minutes on the top. So look at this and convince yourself that minutes were on the bottom of the fraction, which means to cancel them out, we needed to multiply it by a field goal post, which is a fraction, that had minutes on the top. So you have minutes on the top, and 1 minute is the same as 60 seconds. You do the math, and you end up with 3.49 radians per second. Let me actually explain the math just to emphasize this. So the math you were doing, well, we looked at how the units worked out, and we ended up with radians per second. What you would do in your calculator is 33 and a third, so 33.33333, times 2 times pi times 1 divided by 1 divided by 60, and that gets you 3.49 radians. So, yeah, it's a field goal post problem. You'll get good at field goal post problems. So now we know omega, and we want to calculate tangential velocity for each of the beetles. So have we got a formula for tangential velocity? In fact, we do. The formula for tangential velocity is V tangential is equal to R omega. So we just figured out omega, and omega is the same for each of the beetles, but each of the beetles is standing at a different radius from the center. So you solve it for George, you plug in those numbers. George has that tangential velocity. Paul isn't as far away, so his radius isn't as big, which means he has a lower tangential velocity. Ringo's even closer, so he has less. And what is the tangential velocity for John going to be? Well, John is 0 meters away from the center. So when you plug 0 in for the radius, John's tangential velocity is 0 meters per second. John's not going anywhere. He's just spinning in place. So if each side of Abbey Road is 1,500 seconds long, through what angle will each beetle travel in that time, 1,500 seconds? So what's the angle we want in radians? So have we got a formula that can get us the angle if we know their tangential velocity? In fact, we do. If we know their angular velocity. Angular velocity omega, well, your basic definition of that is omega is delta theta over delta t. So solve that for delta theta, and you get delta theta equals omega times t. So plug that in for George. George's angular velocity times that amount of time, and you get 5,235 radians. Plug it in for Paul. Well, Paul's got the same angular velocity. All the beetles have the same angular velocity, so they're all going to go through the same angle. Even John. John goes through the same angle. He doesn't go anywhere, he just spins in place, but he spins in place through that angle. 5,235 radians. So if George is that far from the center, Paul is that far, Ringo and John are that far, how far will each one of them go in 1,500 seconds? So what formula is going to relate how far they go to the angle they go through and their radius? That is your arc length formula. S is equal to R theta. And again, for this to work, theta has to be in units of radians, which we just figured out from the previous slide. So let's solve this arc length S for each of the beetles. George, 796 meters. So if he stands there on the outside and goes around for 1,500 seconds, 796 meters, most of a kilometer. Paul wasn't as far away, so he only goes about half a kilometer. Ringo was even closer, so he only goes about 200 meters. And John, again, doesn't go anywhere. He goes 0 meters. So quick review. How do degrees relate to radians and revolutions? This idea. 360 degrees is equal to 2 pi radians is equal to 1 revolution. Now the cousins. What is the cousin of displacement x? The cousin of displacement x is theta, which is angular displacement, or you can just call it angle. And usually we want that in units of radians. Sometimes it'll be degrees, sometimes it'll be revolutions. So what is your cousin of velocity v? The cousin of v is omega, angular velocity. And what is the cousin of acceleration, a? Alpha, angular acceleration. How is arc length related to angle? So this is the kind of formula that will always be on the footer of your homeworks and everything like that, but worth memorizing. Arc length s is equal to r theta, and I said it a million times through this video, but it's worth emphasizing. This only works when theta is in units of radians. This is not true if theta is in degrees. You have to have your theta in radians. So what are our definitions of velocity and angular velocity? Your basic definition of regular velocity is v is delta x over delta t. So change in displacement over change in time. That means its cousin, the cousin of velocity, angular velocity omega, must be delta theta over delta time. So yeah, think of the cousins. Same idea with acceleration and angular acceleration. Your basic definition of acceleration is delta v over delta t. So the cousin of acceleration, alpha, this guy here, must be equal to the cousin of v, delta omega, over the cousin of t, delta t. T again is its own cousin. So hopefully that helped.